Hi everyone, welcome to today's webinar on glass transition temperature, brought to you by Element Materials Technology. So before moving on to today's webinar, very briefly, for those who don't yet know Element, we are one of the largest independent providers of materials and product testing services in the world. Together, we help our clients to develop better products to take to market, enable them to get their products to market faster than ever before, help them to become more efficient, saving time and money, and through the application of the collective experience and knowledge of our team of over 6,000 engaged experts, we help to minimize the risk throughout their product development and production processes. Again, welcome everyone. My name is Carly Ranks and I will be facilitating today's webinar. It is my pleasure to introduce you to our presenter today, John Moylan. John Moylan has a breadth of experience testing polymer-based composite materials. He joined Delson Testing Laboratories in 1980 as a lab technician and served as president from 1991 until the company was acquired by Element. John is highly regarded for his work on standardization and test methods. He is recognized for his help in the development of the SACMA series of test standards and played an active role with the FAA Fire Test Handbook. John is currently the co-chair of the CMH17 Testing Working Group and an active member of the ASTM D30 and various IPC committees. He has been an active member of SAMPE and serves on the SAMPE Foundation Board, which works to enhance science and engineering education in schools across the country. And with that, I'll hand today's webinar over to John.
Good morning or afternoon. I know at least one person is watching this from Canada on their day off, so happy Canada Day. I picked glass transition as today's topic because it's so important in understanding materials, and it's sometimes misunderstood. Glass transition, or TG, is a reversible transition over the range of temperatures where polymeric materials go from a glassy state to a rubbery state. Glass transition temperature is characteristic of the type of polymer chain, the amount of cross-linking, the chain length, and molecular weight distribution. Since most materials have a distribution of molecular weights and cross-linking, the TG is not an absolute discrete temperature, but it's rather a temperature range. A single temperature is generally reported for convenience, but the material will actually change properties over a range of temperatures. We'll discuss some of the methods for determining glass transition temperatures in this presentation. Because of its close relation to strength and flexibility, it's critical to understand and apply the concepts of glass transition during product development life cycle to ensure polymeric materials, components, and assemblies will function appropriately in the end-use environment. The Challenger disaster is one of the most famous examples of materials used outside the appropriate temperature range. Segments of the solid rocket motors were stacked together, and the joints to join those segments were sealed with a rubber seal. When launched on a cold morning, the seal failed. It was later determined that the material was below its TG and the rubber seals had stiffened, contributing to the accident. So the joints were redesigned with a different seal configuration, in fact, multiple seals, and a different material was selected before launches continued. So at the TG, the polymer chains become more mobile. Because the polymers have a range of chain lengths and cross-linking, this occurs over a temperature range. As this happens, the material becomes less stiff and more resilient. The polymer chains can slide over each other more easily. And so a few other things happen as well. The coefficient of thermal expansion is higher above the TG. Thermal conductivity is generally lower above the TG, but there are enthalpy changes that are evident right at TG. Dielectric loss tangent or dissipation factor generally increases above the TG. So we can measure each of these phenomena using the techniques I'll discuss in the presentation. And the results from the different measurements are not always exactly the same, but they generally occur over the same range. We'll discuss how we might measure TG. The most direct way and the classical way is to run mechanical tests over a range of interest and look for loss of properties. To have any resolution, you have to run very many specimens over very many temperatures, and it just makes this approach impractical. DMA, dynamic mechanical analysis, uses force and deflection data to measure changes in stiffness under varying temperatures. Results are fast, accurate, and easy to determine. Of the various thermal techniques, DMA gives the most easily discernible glass transitions. This is a photo of a dual cantilever beam clamp and a test specimen. The test specimen is this black rectangle here. The center clamp moves up and down. It oscillates in a sinusoidal way. Going too fast there. Oscillates in a sinusoidal way, and we measure temperature as well, and we measure force and deflection as the clamp oscillates. A furnace fits around the outside of this and then slowly heats up over a pre-programmed range. We measure the change in the forces and deflections with temperature, and we get a curve like this. The results are reported as three different curves. The storage modulus or elastic modulus is E prime, and it's this first green curve. You can see that it's fairly steady, and then it really dips down. And that's an indication of where the loss of mechanical properties occurs. And then by drawing tangent lines on these curves, we can determine an inflection point, or what we'll call the glass transition from E prime onset of 44 degrees C. You would just go down here to the 44. This is usually the lowest temperature you see on a TMA, and it's most conservative. And as I said, coincides with the degradation of mechanical properties. Now the E double prime or loss modulus is this blue line, and you can see it goes up to a sharp peak. And it's very easy to determine where the peak is and get a glass transition temperature there. It's a little bit higher, 50 degrees C. Similarly, tan delta, that's the difference in the tangent angle of the force and deflection curves, is also easily discernible, and it's 60 degrees C. So this sample happened to be a room temperature cure epoxy that was post-cured, and we can see all these temperatures are just above room temperature. Moisture will tend to lower TG, and we'll get back to that later, but it's a good time to mention that consistent drying or conditioning is needed to create reproducible measurements. But when you dry or condition the samples, it's important to stay well below the cure temperature of the material. Otherwise, you're going to be imparting additional post-curing to the specimen that the actual part might not see. I also want to talk a little bit about thermal lag. Thermal lag is important to consider in any thermal analysis, but especially DMA, because DMA specimens are usually the largest. The instrument measures the temperature of the air adjacent to the sample or just touching the outside surface of the sample. As the instrument heats, it takes longer for the center of the sample to reach temperature. Because of this lag, it's important that the calibration be performed at the same heating rate as the sample. Ideally, it would be performed with a material that's the same size, mass, and thermal diffusivity as the test material, but generally this isn't possible. Polycarbonate standards have attributes similar to polymer samples and are readily available from instrument manufacturers, but none are officially traceable to a national standards body like NIST. These materials can also change over time or with exposure to moisture. Sandwiches of tin or indium between ceramic plates can be made from NIST standard materials, but lab-to-lab variation can result if these standards aren't consistent. So work is currently being performed in ASTM committees and other places to provide robust, reproducible, and traceable standards. But getting back to the thermal lag, generally the heating rate in a DMA experiment is a compromise. Slow heating minimizes the thermal lag. So if you heat very slowly, the center can come to the temperature of the outside, as you're going along. Faster heating creates more thermal lag and errors related to thermal lag, but because specimens can be changing while they're heated, sometimes that's what we do. Specimens can be curing or drying, and so fast heating eliminates the effects of that and allows you to just measure the glass transition temperature of the material without that curing or drying. And of course, instrument time is important. People want to be able to run more than one DMA experiment each day. So for polymer-based composites, a frequency of 1 Hertz is used for the loading, and a heating rate of 5 degrees C per minute are commonly used in the dual or single cantilever bending mode. And this is fully described in ASTM D7028. A slower heating rate is described in ASTM D4065, and it's usually 1 degree C per minute or so. We can also measure the change in CTE, and we do that with a TMA, or thermomechanical analysis instrument. The instrument uses a small sample on a quartz stage. Here the sample again is black. This is a quartz stage. This is a quartz rod that sits on top of the sample. We use quartz because it has a very low coefficient of thermal expansion itself, and therefore the baseline of the instrument is almost trivial. It's not quite, we correct for it, but it's very low. And then this wire is actually the thermocouple wire that measures the temperature of the specimen. And then a furnace fits around this entire assembly, and again, it heats up. And then the movement of the rod is measured with a LVDT, or linear variable differential transformer. Usually we heat up at 5 degrees C per minute, and the data is reported as a curve where the change of length is plotted versus temperature. And the slope of the resulting curve is the coefficient of thermal expansion, or COLTV. It's actually coefficient of linear thermal expansion because we're just measuring in one direction. Because standards like indium have sharp melting points, calibration is easier to standardize, and there's less lab-to-lab variation. There's a example of a TMA curve. You can see that it's very linear here, and then it goes through a change, or an inflection point. And this happens at the glass transition temperature. This is a higher temperature material, so it's happening at 183 degrees C. It's also worth noting that sometimes glass transition temperatures are well below room temperature. And so if you start your test at 30 degrees C, and the glass transition temperature is down here at 0 or something, you'll miss it. So often we have to start experiments well below room temperature for materials like rubbers and elastomers. TMA can also be used in a flexure or penetration mode. In each of these approaches, a larger force is applied and the probe deflects significantly. Usually we can do that with either a pointy probe, or we can do it using a 3-point bending fixture on a stage with a 10mm span. Specimen thicknesses and loads need to be specified. These methods are written into some specifications, but it's important to get the loads and the thicknesses right, because the ratio of load versus span is important, and if you're not consistent, you get wonky data. A larger scale version of this general approach is ASTM D648, deflection temperature under load. It's commonly called out as a plastics quality conformance test, and you'll see it more often in the plastics community, but it's a much larger specimen that is loaded in bending, and you look for the deflection. And deflection temperature under load is not exactly the same as TG, but they're certainly related. We can also measure change in enthalpy, and we do that with a DSC, a differential scanning calorimeter. A small sample is heated, and the amount of energy required to heat the sample is measured and compared to an inert reference material. Because the glass transition temperature creates a change in properties of the material, the polymer chains reorient, requires a change in energy to heat. And this is shown as a inflection point on the curve. Some of the advantages are, again, the instrument is less expensive than a DMA. Calibration can be more straightforward. This is an example of a DSC curve, and the area of interest is down here. We're heating it up, and then the amount of energy it takes to heat it up changes abruptly. And where it first changes is called the onset of the glass transition by DSC. And this is usually reported because it's most closely related to the loss of mechanical properties. But sometimes midpoint is called out, and sometimes even endpoint is called out. So the onset right here is, again, 140 degrees C. Modulated DSC provides more resolution, and you can see the reversible changes in enthalpy. The instrument heats and cools in oscillation while gradually heating the specimen. So it'll be heating, and it'll go up and down 1 degree C per minute, and then that'll ramp up. And then the instrument measures the reversible and irreversible changes, and it's calculated and plotted. So the top curve, in this case, is an irreversible change. And what's happening here is there's some kind of reaction going on. It's an exothermic reaction, so it could be a cure, or it could even be a degradation reaction. And we can plot the peak points and the onset of that. And then the bottom curve is the reversible change of heat. And if you remember from the very beginning of the talk that we defined glass transition temperature as a reversible transition. In other words, you can go back and forth above and below the transition, and it will happen over and over again. Whereas a cure, it happens once and then it's done, it doesn't happen again. So in this case, we can clearly break out the onset, the midpoint, and the endpoint, and report them that way. For structural composites, the effects of moisture are very important to consider. Moisture will plasticize the material and make it easier for polymer chains to slide over each other, and it thus lowers the TG. So for testing, and I'm talking about mechanical testing of composites, we generally expose samples to high temperature and humidity until equilibrium, and they're weighed several times a week until they no longer gain weight. So this whole process can take several months, so it's usually a qualification test. And we can run DMA or other thermal analysis on wet specimens as well and determine the wet TG. Specific criteria for the weight gain are given in ASTM D 5229. CMH 17, the Composite Materials Handbook, it provides guidance for FAA certification, and it's generally a base reference material. Recommends the maximum use temperature be 50 degrees below the wet TG. So the three most common ways to measure TG are DSC, TMA in the expansion mode, and DMA. And we've looked at all these curves, and now you can see how the TG is apparent. Dielectric spectroscopy is another way you could measure TG, but the methods haven't really been standardized well enough to be in general use in industry. It's more a thing of academic interest and also for cure monitoring. Each of these measurements, though, measures different things and will give slightly different answers because the TG is a range of temperatures where the polymer properties are changing. So it's important in both design and problem solving to kind of understand that you're dealing with a range. At Element, we perform each of these tests at laboratories around the world. We have labs in the Americas and in Europe. We generally use common procedures, common lab accreditations, and we have access to experts around our network. So I'm going to turn it back to Carly for questions and answers.
Thank you, John. So yes, as he mentioned, that brings us to our Q&A session. It looks like we've had a couple questions come in throughout the webinar. So if you're ready, John, I will begin passing those along to you. And again,
Sure.
If anybody has any other questions, please feel free to submit those on your panel. So yeah, the first one is, what are the implications of TG for structural composites?
So structural composites are made of a resin and a fiber. Generally, the fibers are like carbon material or glass, and they're not affected by TG. So properties that are fiber dominated, like a tensile strength, where all the fibers are in the 0 degree direction, isn't affected by TG very much. In fact, a lower modulus resin might even help the 0 degree properties. But in compression and shear, TG is very important because these are resin dominated properties, and we're really counting on the resin to transfer loads between fibers and between layers of the composite. And so for resin dominated properties, the TG is very important.
Great, thank you for that. And then what are some other factors, so I assume this means other than moisture, that could affect glass transition temperature?
So how a material is cured is important, whether the cure is complete. Also exposure to other fluids, could be hydraulic fluid or jet fuel or other things like that can also impact TG.
Awesome, thank you. And can you increase the overall glass transition temperature?
If with a standard formulation, say, you can increase it some by making sure that the material is fully cured and fully dried. But beyond that, you can't do much other than reformulate to a little bit different polymer chain and polymer material.
Okay. And there's some other ones that have just come in, so I want to make sure I cover those as well. So how about testing TG by rheometer? Sorry if I pronounced that.
Yeah, so no, that's right. I didn't mention that. It's sort of similar to DMA in that you're stressing the material and measuring loads and forces, and I should say loads and deflections. Usually the rheometer is in torsion, and it can be like the material is between a cone and a plate, or sometimes between two plates, and one plate is turning compared to the other one. And that's actually more useful if you want to study the cure advancement of a material. You want to see how the viscosity changes as it cures, but you can measure glass transition temperature with it too. It's a little bit less handy for most labs, is why I didn't mention it.
Okay, and then next one is, can you explain more of the difference with TG when tested with DMA? Why the range in temperature?
Why the range of temperature between the E prime loss modulus and the other measurements? I don't know the material science polymer theory reason for that. I'm sure that I'll consult with some other people and maybe we can answer that as we respond to the webinar. But generally, the E prime number is always the lowest one, and that's the loss of the elastic modulus. That's the, the primary loss of stiffness. And so that's the one that we usually pay attention to.
Okay, yeah, and yeah, just this goes for all questions. If at all, John, you don't have the answer now, we can definitely reach out after and follow up with people as well. So the next one is how can we measure the heat capacity from the DSC curve?
You can, there are ASTM standards to do it, and with the modulated DSC, it's much better. And you use standards where you know the specific heat. Usually a sapphire is the most common standard, and you measure the mass of the sapphire and you know the specific heat. And so you run the sapphire standard against you also have an inert standard in there, and then you run your unknown material and you can determine a heat capacity that way.
Okay, great, thank you. And this next one is, when you get into the rubbery state, is it important to know how rubbery?
I suppose it depends on the application. It also is important to know how resilient a material is. You can have a material that's sort of soft and rubbery, and you try and bounce it, and it bounces up like the old super balls, or you can have one that just kind of lands and goes thud and just doesn't bounce. And that kind of behavior can be modeled on DMA. And so, and then you can also measure, things like hardness and elongation and, other properties using mechanical tests. But when is it important? It really depends on the application.
Great, thank you, John. And then got another one here. So could we change or manipulate TG dramatically by introducing additive? And if so, would you share with us some examples of such case?
I don't think, and this is just based on my really limited experience. So I think it depends on the particular polymer that we're talking about, but I think you're not going to change things much by, adding, an inert filler like, calcium carbonate or carbon black or things like that. You will increase it if you can somehow increase the cross-linking of the polymer, but that's not so much an additive as changes in maybe the catalyzation of the Cure reaction. We'll see if that's another one I may get some of my colleagues to help me expand on, and we'll respond by email.
Yeah, okay, great. And then let's see, I just have a couple more here, and then I think we are about done. So what are the implications for electronic materials?
Yeah, so TG is really important in the electronics industry. With printed wiring boards, the printed circuit boards are multiple layers with different interconnections, and the layers are interconnected with each other by plated through holes or vias that are made out of copper. And so as the printed circuit board material itself has a much higher coefficient of thermal expansion than the copper. And as the material goes through thermal things like soldering and solder rework, and then even in some applications like satellite where it's being cycled thermally, the circuit board is expanding and contracting, and it can cause these copper interconnects to crack. So you want to use a printed circuit board material that's below its TG, because then the coefficient of thermal expansion is lower. And so for those high, thermal cycling applications with high reliability, it's why you see people use polyimide boards and not epoxy boards. Similarly, in microelectronics, the microelectronics packaging is important in that it expands and contracts as the chips cycle and heat and cool, and you want to minimize that. So again, you want to use a material below its TG.
Great, thank you. And this is actually the last question. So how is Element coping with the COVID-19 crisis?
All our labs are currently open. We had to have a few labs here and there closed for a few days, but generally our labs are open. All our lab technicians are working with proper social distancing and personal protective equipment and a lot of disinfection. And we're open to service our customers as usual. Some of us, like me, are working more from home, just so that we're less, to create more space in the lab for the guys that actually have to run tests. But we're able to service our customers.
Wonderful. Thank you, John. So that is actually all of the questions for today. If anyone would like to reach out with more questions, please feel free to contact John, or you can contact myself and I will pass those along to John as he is the expert. But again, I just want to thank you all for joining today's webinar regarding measuring glass transition temperature. Please be sure to follow us on LinkedIn or subscribe to our events on element.com to hear about our upcoming webinars. And I hope you all have a wonderful day.